Hello folks. So in the last video, we created a particle light system like this one you can see over here. Now in this video, we will implement a grid system to create this, and we will not be comparing each and every particle like we were doing last time because that is very inefficient. Because once we add one or two particles, it needs to be compared with every other 400-500 particles, which will make our system really slow. We won't be able to add a lot of particles like that, and the lesser the particles, the lesser complex behaviors, and we won't be able to make artificial life like this. So we will use grids, and we will only compare particles within one grid and neighboring grids. The number of comparisons will be much less like this, and yeah, we can hope to get more interesting and complex behavior like this. So yeah, let's go back to VS Code and let's see how we can code this one. So we are back to our VS Code, and I have a very self-explanatory index.html file over here, and we have a script.js file also, which is connected to this one, and we have a canvas element. And if I go to the browser, this is how the canvas looks like. So we'll go back to our script.js file and start writing our code. We'll start by defining the canvas. So the canvas equals to document.query selector canvas, and then we have to create our context. So const ctx equals to canvas dot get context and 2D because we are making 2D drawings, and then let me define the width and height of the canvas. I'll give both to be 500. Now what we need is some grid measurements. What do I mean is I need something called a grid side. Let me give it 50. So if I go back to a browser, this is how the canvas looks like now, and this is 500 cross 500, and what I want is a 10 cross 10 grid. That is 100 cells. So that means each cell is 50 cross 50, and which is basically our grid side. So we will also have something called grid calls. Now we can write it as canvas.width divided by grid side, but it's so simple, I'll simply write 10. And same goes for the grid rows. Now after this one, we will have our, as usual, class called particle. And inside we will have a constructor and many other things, but many of this code is actually the same as our previous code from our cells. So here we have class called particle, inside constructor, this dot x, y, color index, many things. And we also had a universal friction. Maybe we will also use this one. So there is no need to write it again. We can simply use our old code. We will simply cut, copy, paste. So what we will do is we will, instead of that, we will try to implement our grid code first. So before doing anything, we need an animate function because the particles need to animate. So we'll do a request animation frame animate, and let's call the animate yes. And now lastly, nothing lastly. We have grids, we have grid rows and columns and many things, and we need to draw the grid. That is what I want. So how to draw the grid? So we'll do a ctx dot begin path, and then ctx dot let me give a stroke style as white because we are drawing in black. Ctx dot line width, let me give it as 1. Now what is a grid? So the grids are basically cells, right? So there will be 100 cells. So starting from this one, 1 2 3, like this one. So it need to be done inside a loop. So we'll create for loops, and not one for loop, we'll need two for loops. So let I equals to 0, and I should be less than grid calls, and then I plus plus, and then for let j equals to 0. Now j should be less than grid rows. Now in this case both are same, j plus plus. Now whatever I'm doing should be happening inside this. So line width is 1. Now we'll do is ctx dot stroke rect. Now starting point, which is the starting point? So starting point is I multiplied by grid side, comma j multiplied by grid side, comma, this is the grid side is the width and height, this one, and then ctx dot stroke, and lastly ctx dot close path. Very, very simple. So this is what we have. Now we cannot keep it over here because inside the animate function, as we generally do, we clear our canvas so that we can basically we can move our particles. Right now we are not doing that, but we will definitely be doing this in the future. So this is something that we will need, canvas dot height. So this for loop should be after this. So now we have a grid. In the end, we will not show this one, but this is important for now. Now, after this, uh, what do we need to do? So, basically, we will have a for loop that will loop through particles. So, we need to have something called particles, and here we will put particles inside. I mean, this is like common sense. We have to insert particles, right? So, what we will do? So let's insert some particles. So after the particle for, let me do it like this, for let I equals to 0, and let's insert 100 particles and I plus plus. Now, what we want to do here is uh, the particles need to have like some x position and y position and some color. And we are also giving some color index. So let me just copy it from over here. Mm, I don't want to write. So here we are inserting 100 red, 100 blue, and 100 green. So let's take these three and let's bring it over here. And yeah, so this is what we want to do. Now the issue is the class particle doesn't have anything like this for now. So we can simply copy that also. So we'll go here and let's copy the whole constructor. There can be something more also, but for now, let me just copy the constructor. Yeah. And because we are copying, let me also copy the draw and the update. So let me also copy these two functions and let's see. Right now we will not get anything because we are not drawing, we are simply adding. Now inside the animate, what we will do is basically um, we have to check, like we have to loop through the particles and we have to draw them first and then we can do other things. So first things first, what I will do is let I1 equals to 0, then I1 is less than particles dot length and then I1 plus plus. Now here inside let P1 equals to particles I1. Yes. And now first things first, P1 dot update CTX. Now let's see we get something or not. We still don't have anything. Let me open the console and let's see. So the issue is there is no universal friction. Yes. So we have to add a universal friction. So let me just come over here and add the universal friction. So const universal friction equals to 0.05. Now let's see. Yes. So we have lots of particles scattered around. Now none of these particles are moving. And why they are not moving? They are not moving because the Vx and Vy is 0 and we are adding the forces, but there is no force. That's fine. And before adding any force, we have to implement our grid. So here we are doing a p1 dot update, and that's fine. And after this, we generally do a force on the x and force on the y. Let fx, fy, and then we create another loop for let I2 equals to 0 and I2 is less than we cannot do a particles dot length because we don't want to search through all the particles. So instead of that, what we will do is we will check what all particles are like around the particle P1. So let's check all particles around, or let's simply write all particles equals to get all particles, let's say in grid and surrounding grids. It should be in cell and surrounding cells, but anyway. And here what we will do is we will pass the p1 dot grid index and p1 dot so grid index. So one is the x and another one is the y. So this is not something that is defined, I believe. So yes, this is something that we need to add. So this was not present last time, and that is fine. But in this case, we have to add it. So this dot grid index equals to math dot floor of what, x divided by the grid side, right? Yes. And now for the y. So this dot grid, let me do in dy, creative name, I believe. So this is y divided by grid side. Yes. And then radius, vx, vy, maxwell, fx, fy, everything is fine. So now, so we have to add this one and grid in dy, this. And then for the I2, we need to look through all particles. That's all. And I2 plus plus. So here the particles count will be significantly less than the total number. So here we have 300 particles we are adding, but we will not be checking through 300 particles here. That is for sure. So we have to implement this function. So what is this function? First of all, let's try to understand. So let me write the function. Function get all particles in and surrounding grids. And here we will pass gx and gy, let's say gx and gy. Now what is this? I mean, how to find this? So to find this, we need to find particles in the current grid. So for example, if I go here, Acha, so get all particles in and surrounding grids is not defined. Yes, that is true. It is not defined. Okay. So let's say I'm in this grid. So in and surrounding grids means I have to find all particles in this grid, in this, in 9 grids in total. And to do this, I will start by writing a function, and this function is get all particles in grid. What this means is we want to get all the particles in the current grid. So for example, here we were taking this one or this one, whichever one is this. So for example, let's say take this one, this is the center, and we will take the surrounding 8. So get all particles in grid means we will take these 3 green particles. So that is what we mean by this. And how to get this? It will also take gx and gy. And here um, we have to return something. So what we will return? We will return all particles. And all particles is basically particles dot filter. Filter. We will have a p, and we will only return p when if our p dot grid index equals to gx and our p dot grid in dy equals to gy. In that case, we will return p. Otherwise, we will not return anything. And lastly, we will return all our particles. Now, there will be 9 functions like this for getting particles in each grid. This is the first function for getting the particles in one of the grid. And for all particles in and surrounding grids, here what we will simply do is we will simply add all the particles that we get and we will return all of them. So it will start by returning get all particles in grid, and we will pass the gx and gy. And what will we have to do is there will be 8 more functions like this. So 1 2 3 4 5 6 7 8. And this one will be get all particles in up grid, and the next one will be down grid, next one will be left grid, next one will be right grid, and then we will have up right, up left, down right, and down left. So up right, then comes our up left, then comes down right, and then down left. Now the remaining 8 functions doesn't exist right now. We only have one function, and hence there is an issue. So as we can see, so many things are not defined. So what we can simply do is we can make the functions. That is what we can do. So let's start by one. So get all particles in upgrade. So how can we get all the particles in the upgrade? Okay, let's try to think. So let's say we are here and we want to get the particles of here. So we are passing the gx and gy, which belongs to this cell over here. So what is the gx of this cell? It is the same as this cell, but the gy is -1. So it is actually very simple. So here for the upgrade, what we have to do is let up gx equals to gx and let up gy equals to gy -1. But let me tell you, this is not so straightforward because let's say the particle is in this cell. Now, what is the gy for this? The gy is 0. So, what is the top cell? The top cell, the gy will be -1. But that is not true. The top cell gy is actually this one. So, this is actually 9. So, here we have to write a condition. So, the condition is something like this. If gy -1 is less than 0, if this is the case, then the gy will be grid y is actually rows. So rows -1. Otherwise, it is simply gy -1. And in the all particles, instead of equating with gx, we have to equate with the up gx. And actually, we don't have to do this thing. We can simply remove it. We can simply call this function. So what we will do is let up particles equals to get all particles in grid, and here we will simply pass the up gx and the up gy, right? And instead of sending all particles, we will send the up particles. Yeah. So very similarly, we have to write 7 more functions. Now I don't think it's wise writing these things one by one because all the functions will be similar, and we only have to take care of the up gx and the up gy. So I have already written all these functions, so let me simply copy them, and we will just go through them once we have it. So let me take it and let me copy. Yeah. So we have written up to the up. Then it is for the down. So for the down, again the gx is same and the gy becomes +1. And we are getting that. For the left, the x value is changing, the y value remains same. Same for the right. And for the top right, top left, down right, down left, both the x and y are changing. And accordingly, we are getting all the values. And hence, we are no longer getting errors. We are getting all the particles. Yeah. So now what we need to do is we need to now take care of the forces. That was absent till now. So for the forces, we need the force and the distance functions. So we'll go there and we will take the force and the distance. Let's keep it over here. So we have the force and we have the distance. And now let's go back to our animate once again. Where is our animate? Here. Yes. Let's keep the animate down because mm, otherwise it will be difficult. It will be difficult to track it. So let's keep it down because we have written so many lines of code. Now we may fail to find the animate. That will be terrible. Anyway, so we have the x fx fy is 0 for now. All particles we are getting like this, and now we are looping through. We are getting one particle and we are looping through the particles in the surrounding grids. So for one particle, we are maybe comparing 10, 20 particles. Previously, we are comparing 300. So it's already a much, much better algorithm, I would say. So now, here again, we have P2, and P2 is basically particles I2. Now, here there is one issue actually. Previously, we were doing something here when we were comparing I1, we were checking if I1 and I2 is same, we are not checking. But in this case, we will not be able to do that because all particles and particles are two separate arrays. We will not be able to check if the particles are same. So in case the particles are same, the only way to check that is if the distance is 0. So in the distance, so where is our distance function here? So x distance will be 0, so y distance will be 0, square distance will be 0, and this distance will also be 0. But there is a problem in the force. So if the distance is 0, so 10 by square distance, it becomes a big issue. So, so we have to take care of that. So if it is the same particle, the distance will be 0, and hence we need to take care of the force. So what we want to do here is, if let's say distance is not equal to 0, only then you do all of these things. But otherwise, if let's say the distance is 0, what we will return is return force x to be 0, force y to be 0, and force to be 0 again. So basically, if it's the same particle, keep the force as 0. That's all. So force, and distance, we got this. And now we can compare. So in the animate function, we have I2, and inside the I2, let's take the distance between I1 and I2. So distance of P1 and P2, and then we will take the force between P1 and P2, and then we will check if distance is not too small. So if distance dot distance is, let's say, is greater than 0, and distance dot distance is less than, let's say, P1 dot radius into 10. So if the radius is 2, let's say within a distance of 20, we will have repulsive force. So Fx minus equals to F dot force x. Let's say the repulsive force is very strong, so we'll multiply it with 5. So F dot force y times 5. Else, we want, what we want? We want the force to be added. So Fx plus equals to F dot force x, and Fy plus equals to F dot force y. Now that's not all. We want to use the interaction matrix also. But for now, let's keep it like this. And after the if else is done, after the for loop is done, we want to assign p1 dot fx equals to fx, that we got, and p1 dot fy equals to fy. Right. So now let's see, we have some interactions or not. I don't see anything. So let's see if the particles have any p1 or p2 or not. Maybe they don't. Uh, yes, they have these things, but why are they not interacting? Okay, anyway, let me add the interaction matrix again, and then we'll see this thing. So, what is the interaction matrix? So we have three kinds of particles. So what will be the force, like the forces between each particle? So that is basically our interaction matrix. So we'll define it at the top, somewhere over here. So this is our interaction matrix, and here we will multiply that with our respective matrix. Mm. Maybe the forces are so small, that's why we are not seeing anything. So if I make the forces 20, let's see. Do we see any changes or not? Still no changes. It looks like they are totally like they don't have any will to move. It looks like that. Anyway, let me add the interaction matrix. Mm, hmm. So here we are adding the forces. Now, apart from adding the forces, we want it to be factored with the interaction matrix. So interaction matrix. So which particle is this? This is the I1 interacting with I2. So P1 dot color index and P2 dot color index, and same for the Y also. P1 uh, interaction matrix, P1 dot color index, and p2 dot color index. Yes, and if I check my for loop, so here it's very clear red, blue, and green. Right. So above the interaction matrix, so we have red is 0, then red, blue, green, right? So blue is 1 and green is 2. So if red and red interacts, it is 1. Blue and blue is 1, but green and green is minus 3. So green is strongly repelling green. Now let's add red and let's take this one. So red, 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 blue. So red is repelling blue, but on the other hand, blue is strongly attracted to red. So this is something that we are expecting, but we are not getting. So let's try to find it out why the particles are not moving. And there is actually a very silly issue why this is not working. And that is for the second loop, we are looping the all particles. Ideally, it should be all particles dot length because all particles is not a number. Now, if we can see some particles are a little bit moving and interacting, but it's not much, and we can definitely fix this. And also, I think the blue particles and the green particles are too dark. So I want to change their color. So what I will do is let me come over here. So instead of blue, I will use yellow, and instead of green, let me use light green. Yes. And let's take 200 particles now because we are using grids, and I believe we will not have any issues. Now let's see. So we have lots of particles, and they're kind of moving a little bit more. Some particles are coming very close and trying to have like form interesting behaviors. Now particles are not able to move to like very close um, because there is a strong repulsive force, especially the reds. The reds are having an issue moving close to each other. So let me do one thing. Let me do some mischief. For the reds, let me make the attraction among each other as 3. Okay, still the reds will have problems, that's for sure. But we are definitely seeing some interesting behaviors here. Hmm, it already looks like a cell. Let me do one thing. This white grids doesn't really look good right now. So let me remove that. So I will simply go to my animate function and I will simply comment it out. Where is this part? Because we want to see more particles and less grids. Yes. Hmm. So how does it look? Does it look like a cell? Okay, the reds are very having a lot of difficulty. So the greens are almost non-interactive. I mean, if they are close, they are interactive. Otherwise, they're not. So let me do one thing. I think the repulsion is too much. We shouldn't have that much repulsion. If I do a little bit less repulsion, maybe it will resolve a lot of issues. So here, let's make it 5. Now the reds will come more closer. And we are having a lot more things forming here and there. Hmm. Yeah, I think this is better than the other one. Some, some organism-like things are forming. I'm not exactly sure. These look a little bit like flowers. Um, we can create a board of interactions over here instead of just doing it like this. Let me also try one more thing. The repulsions should be 3 instead of 5. Now what will happen? Hmm. So they're not able to come very close. That's for sure. So p1 dot radius 3. Let me make it 3. Now let's see. Hmm. Now something else is happening. Anyway, I will leave it up to you. You can add more particles, and yeah. So now many things are also moving. Yes. So yeah, you can definitely try out new things with this one, and I will also create a lot more videos like this because particle life is something that is for me that is very interesting, and we'll see. We'll try to make some more interesting behaviors, and let's see. what comes out of it. And yeah, we are also doing the neural network with JavaScript, and we will also gradually be trying to add. We need some more ideas on this, on how to make them learn. Maybe we can define some behaviors that once they form a cell, they will have a different sort of behavior. Um, right now, it's totally random, and these are totally not expected. And we'll try to make some better behaviors. Yeah. So that's it for this, folks, and we'll see you next time with another very interesting video. Let's see what that could be.